This is your presenter, Asloob Mudassar, and I am presenting slide number 1 of the course on Atomic and Molecular Physics, abbreviated as AMP. The topics that will be covered today are basic principles of spectroscopy, emission, absorption spectra, hydrogen spectrum, Ritz combination, etc. These topics will be covered, and this is a new course, and this is the first lecture of this new course. Basic principles of spectroscopy. The purpose is the investigation into the electronic structure and the composition of atoms and molecules. So if you want to investigate into the structure of the atom, you need to explore, or you need to investigate the electronic structure of the atom, because the electronic structure will provide you the information about the composition of atoms and molecules. Through the analysis of spectra, so you see that the spectra could be in the visible, in the IR, that is infrared. The spectrum could be in the ultraviolet, microwave, radio wave, etc. So you see that in the analysis of the electronic structure, not only some more, for example, more than one or two electronic spectra could appear. For example, the electronic spectra in the visible, in the infrared, or in the ultraviolet, for example, may appear in the investigation of an electronic structure, for example, in an isolated atom. So these are the spectra these are the name of the possible spectra, and the types of the spectra are line spectrum, band spectrum, continuous spectrum. The line spectrum consists of single lines and are associated typically to isolated atoms. So if you are investigating the electronic structure of an isolated atom, you will encounter in the spectrum only single lines associated with the structure. There could be a band spectrum also, or band spectra, consist of a group of a large number of spectral lines which are very close to each other and are generally associated with the molecules. So in the molecules, you will simply observe the band spectra. Then you have the continuous spectrum. Continuous spectra emitted by radiant solids or high density gases. So if you have the radiant solids or you have the high density gases, then you will encounter continuous spectra. So you see that our topics in this course will be to the analysis of, we shall talk about the line spectrum, band spectrum, and the continuous spectrum very frequently. So the spectrum can be, as we have mentioned earlier, that the spectrum in the different regions of the spectrum is very broad, starting from the radio frequency. For example, on the left we have the radio frequencies and up to the gamma radiations. And these are the regions that I have given for the spectrum. Some regions may slightly overlap. So we have the radio frequency, we have the very high frequency, we have the ultra high frequency. Then of course we have the wavelengths related to radar. Then we have the microwaves. Then we have the infrared. We have the visible spectrum, ultraviolet spectrum, X-ray spectrum, gamma radiation spectrum. So you see that the visible spectrum is you see that narrow spectrum in comparison with others, and all these spectra are not to the scale. So their dimensions could vary. So if you want to consult a very precise spectrum of spectrum variations or spectrum distributions, you can consult other resources. But here I am just want to give you the names of these spectra. And some regions of this spectrum is slightly overlap. So these, for example, if you are measuring the spectra in the visible, or for example in the microwave or in the IRED, in the infrared, then of course these spectra may be referred to as or in the UV or X-rays, these may be referred to as the optical spectra. And optical spectra are usually have two categories, that is the emission spectrum and the absorption spectrum. The emission spectrum by name is obvious that we want to measure or we want to detect the light which is emitted by the substances. And in the absorption spectrum, our spectrum will be based on the missing wavelengths, that is on the absorbed wavelengths by the material which have not emitted in the direction of our detecting instrument. So if material has absorbed some wavelengths and those wavelengths are not reaching to our detector, then we shall say that we are recording the absorption spectrum. And in the emission spectrum, we measure all those wavelengths which are emitted by a substance, and those wavelengths reach to our detecting instrument. So let's talk about the emission spectrum. So there are two main categories that we can split an optical spectrum into the two. For example, it could be emission spectrum, it could be the absorption spectrum. And of course, these two will be opposite to each other. For example, in the emission spectrum, all the wavelengths emitted by the light will be emitted by a substance will be available for analysis, whereas in the absorption spectrum, only the missing lines, all the other lines except those lines which are absorbed by the material, or you can say that the missing lines will be recorded in the absorption spectrum. So in the emission spectrum, substance is first given energy. So the energy to a substance is given by many ways. For example, by electron collision, by light, that is by flash lamps, by passing a current through the material. You can energize the electronic states of the substance, or by illuminating the substance with an X-ray, that is X-ray excitation. So these are the possible ways by which energy can be given to a substance. That is by through electron collision, by light, or by flash lamps, by passing a current through the material, or by X-ray excitation. The light emitted by the substance is then detected. So this is the more important point, is that the light emitted by the substance is then detected in the emission spectrum. Now let's talk about the absorption spectrum. As I have mentioned, that in the absorption spectrum, we record all the wavelengths except the missing wavelengths, except the wavelengths which were absorbed by the material and emitted in different directions from the detector. So those wavelengths are not reaching the detector, and we shall say that such a spectrum is referred to as the absorption spectrum. If a substance re-emits the same wavelength it has absorbed, the process is called resonance fluorescence. So resonance fluorescence means that you illuminate, for example, a substance by some wavelength, and the substance will re-emit the same wavelength. Then such an emission is called resonance fluorescence emission. Now you see that this is a setup that we can use in order to record the absorption spectrum. So for example, this is a sodium lamp on the left hand side, giving you some sodium light, and this sodium light is collected by a collimating lens and is converted into a parallel beam of light. This parallel beam of light will pass through a glass chamber or a glass sphere. This glass sphere contains sodium vapors in metal form, which were the metal was heated using a burner. You can see that the burner is providing heat to the glass chamber and ultimately to the sodium metals, or the sodium metals contained in the jar, and sodium metal will be converted into the sodium vapor. And you see that I have shown sodium vapors in the chamber. These sodium vapors will of course absorb the light for incident on the chamber, and the light is emitted in different directions. You see that this is the fluorescence emission. That is the same wavelength which is absorbed by the sodium vapors. Those wavelengths are emitted by the sodium vapors in all directions. But you see that it is very hard, and a very small amount of light may go towards the detector, or you can say that almost no light will reach to the detector, or a very insignificant amount of light will reach to the detector, and this detector will see that the wavelength is missing. Because you see that if the sodium chamber is not contained over here, this yellow light will reach to the detector, and the detector will detect the sodium light from the lamp. But if you place the chamber, then of course the sodium vapors will absorb the light and will emit in different directions, as you can see that I have indicated with these arrows that the lights will be emitted in different directions, but not in the direction of the detector. So this light, that is a sodium light, in the absence of this chamber which was coming to the detector, now will be missing, and the detector, this will be referred to as the absorption spectroscopy. It means that there is something within the chamber that has absorbed the sodium light and has emitted in different directions, but not in the direction of the detector. And so by this one you will see that you can investigate that these vapors have absorbed the wavelength which was incident on this one. So it means that if you have any general vapors containing a broad spectrum, you can illuminate those spectrum with the different known wavelengths, and you can observe that whether your detector has detected those wavelengths or not. If the detector has not detected a particular wavelength, it means that that wavelength is missing from the spectrum. So by using single wavelengths of different single wavelengths of a variety of wavelengths to any general vapors, you can measure the missing. You can observe that if some wavelengths are missing and not reaching the detector, it means that you can say that the vapors in that material has absorbed that particular wavelength. So this way you can detect that your vapors contain different wavelengths, different matching to those wavelengths, or different spectra of those wavelengths which are missing. So this is the setup of the absorption spectroscopy. And you see that sodium metal, so let me abbreviate very simply, that the sodium metal is heated in an evacuated glass sphere. The sodium vapors absorb the light from the sodium lamp and emit the same light as resonance fluorescence in all directions, but almost negligible light in the beam direction will reach the detector. So the detector will record that a particular wavelength which was illuminating the chamber is now missing, which means that the atomic structure of the vapors correspond to the emission of that wavelength. Spectra are measured in several wavelengths. Now the question is that can we use this spectrum for emission spectrum? Yes. If your detector is not placed, here you see that in the absorption spectrum, our detector is placed in the path of the beam. That is, if this glass chamber is not there, then of course the light will directly illuminate the detector. But now, if you place this detector anywhere around this glass chamber, then of course you will detect the same light which is emitted by this material, and that will be the case of emission spectroscopy. So your detector will then record the emitted wavelengths from the vapors, and then you can infer information about the wavelengths through the emission spectrum. So if you place your detector anywhere except in the present position, then of course you will be detecting the light emitted by the vapors as a resonance fluorescence, and then of course this will be the case of emission spectroscopy. So by placing the detector anywhere, your setup will be ready for emission spectroscopy. But if you place the detector as shown in this figure, it will be the case of absorption spectroscopy. Now spectra are measured in several units. For example, in wavelength unit, you can measure the spectrum. The spectrum can also be measured in units of frequency, can also be measured in units of a wave number, can also be measured in units of energy. So we are briefly talking about these measurements. So in wavelength measurement, when instruments are based on a diffraction grating are used, which we call as a grating spectrometer, then of course for such a grating spectrometers, the wavelengths are usually the measurement is usually given in terms of the wavelength. For example, it depends upon the use of the instrument. So using a grating spectrometer, we measure the wavelengths in terms of wavelength. We specify our measurements in terms of wavelength units. The measured spectrum is compared with a calibrated spectrum. So if we are using a grating spectrometer, then of course in such a spectrometer we require a wavelength which is referred to as the reference wavelength, or we may call it as the calibration of the instrument. So when we do the calibration of the instruments, we know that at these at so and so angles we are measuring such and such wavelengths. So the calibration of the instrument is required. So once the instrument is calibrated, then of course we know the position of different wavelengths in our instruments due to the reference wavelength, and then of course any unknown wavelength which will enter our spectrometer can be recorded easily, can be recorded and marked. So such calibrated wavelengths are used in the past. In the past, we have been using a Krypton 86 line as a reference line. So it emits that is a Krypton 86 will emit very many wavelengths. So one wavelength which is which we call as a yellow line will be used has been using as a reference line. So a yellow line from Krypton 86 atom is one wavelength standard, and that one wavelength standard was used in the past. And the wavelength that was coming out from the Krypton 86 through the vacuum was lambda vacuum is equal to 6057.80211 angstrom. And angstrom, you see, that is the unit which is equal to 1 angstrom is equal to 10 to the power minus 10 meter, and this is in wave number. And wave number, you see, that is the reciprocal of the wavelength, that is a new number, that is the wave number which is represented as a nu bar is equal to 1 over lambda. And if you divide if you take the reciprocal of this quantity, you will get that you will get the wave number equal to 16507 0.6373 centimeter inverse. So you see that here we have specified the wave number in centimeter inverse. But you know that wavelengths are usually specified in vacuum. So wavelengths are usually referred to vacuum, which we call as a lambda vacuum. But you see that if we want to calculate the wavelength in air, then we are using this formula, that is lambda air is equal to lambda vacuum divided by the refractive index of air, which we call as N air. And this measurement can be done at 15 degrees Celsius or 760 torr of atmospheric pressure. So if you are carrying out your measurement under this temperature and pressure, then of course the wavelength of the vacuum can be converted into N air and with divided by the refractive index of the air, and then you can specify such a wavelength as N air. So N air, when we are talking about the lambda air, that is it means that we are carrying out our measurements at 15 degrees Celsius and 760 torr of pressure. So N air, that is the refractive index of the air, is of course the function of a wavelength of light. So at different wavelengths, the refractive index of air will appear to be a different quantity. For example, at a lambda vacuum, that is at a vacuum wavelength of 6000 angstrom, the refractive index of the N air is found to be 1.002762. So this is the refractive index of the air at this wavelength. So if you are using different wavelengths, then of course the value of the N air will be different. So you have the value of the lambda vacuum over here, which is a 6057.80211 angstrom, and in lambda air the same wavelength in air will be equal to 6056.129451 angstrom. And you can see the difference between these two quantities, that is the difference is of course significant, we can see. So you can specify your wavelengths in vacuum, or you can give your wavelengths in air. Now we talk about the frequency units. In frequency units, the frequency does not depend on medium. That is same in air and in vacuum. So this is the advantage of using the frequency. That is, the frequency will remain same in air and vacuum. So we don't need to give over frequency value in vacuum or frequency value in air. The frequency will be the same both in vacuum and in air. So this is of course has some advantage over the previous measurements of wavelength. So frequency does not depend on medium, that is it is the same in air and in vacuum. So this frequency, you see, that is given by C over lambda vacuum It is also given by C over, so lambda vacuum is given by N air multiplied by lambda air, which you can find out from this expression, that is lambda vacuum is equal to N air times lambda air from this one, and you can substitute this over here, and so you have the frequency which is equal to C over lambda vacuum is equal to C over N air into lambda air. So you see that nu would not depend upon the value of a lambda vacuum or the lambda air. It will give you the same value in both vacuum and air. So nu is has advantage in this sense that you don't need to specify the value of the frequency in air or in vacuum. It will be the same. The next quantity that we are going to give the units of measurement of the wavelength in wave number. So wave number is also very frequently. So the spectra are most frequently cited in wave numbers. So you see that wave number, because this has a historical advantages also. So the spectra are usually given in the wave numbers, and wave number is defined by nu bar. So if you have the frequency and with the bar over there, that is a nu bar is the wave number, and this is given by nu over C. And this nu over C, you see that is equal to 1 over lambda vacuum, because you see that C, that is the velocity of light, is defined in vacuum. So we have used the wavelength over here, vacuum. So nu bar is equal to nu over C is equal to 1 over lambda vacuum, and this lambda vacuum now can be specified in terms of the N air and lambda air, which is equal to 1 over nu, which is equal to 1 over N air times lambda air. So you see that nu bar is also not influenced by the value that you are measuring. It is the same. It has the same value in vacuum and in air. So you don't bother about the medium in which you are measuring it. So the wave number is also a very popular quantity, and as mentioned earlier, that most of the spectra are cited in wave numbers, and the units for the wave numbers is usually specified in centimeter inverse. The wave number nu prime is proportional to the energy. For example, you see that this expression is equal to h nu, that is the energy of a photon is given by this through this expression, and you can multiply C and divide it by C. You have hc multiplied by C nu over C. This nu over C is actually nu bar as defined. You see that in this definition, this is the definition, and we have introduced nu bar. So you see that h and C is constant, where h is the Planck's constant, C is the velocity of light in vacuum, and then you see that nu bar, which is the wave number, is now directly proportional to the free energy of the photon. So E is directly proportional to the wave number. So that's why the wave number has the advantage that it also gives you the information in terms of the energy of the photons. Now in units of energy, for example, in units of energy, we shall be using electron volt. Usually some spectra are mentioned in terms of electron volt in the previous history, if you look, and so it is the energy unit is also used today. So the spectra are also specified in electron volts, and this electron volt is equal to 1 electron volt is equal to 1.602 into 10 to the power of minus 19 joule. So you see that you can also express this joule in terms of m naught c square. For example, if you use the formula that is E is equal to mc square, then of course you can write that formula for the energy, for the rest mass energy of an electron, which is equal to E is equal to m naught c square. And you see that m naught c square also has the unit of joule. So if you divide this J with m naught c square and also multiply with m naught c square, then this J and m, you can specify the value of m naught c square, where m naught is the mass of the electron and c is the speed of light. So specifying these two values, and 1.6 multiplied by 10 to the power minus 19 will be divided by the value of m naught, will be divided by the value of c square. Then you will get this quantity, which is 1.96 into 10 to the power minus 96, and then of course you have expressed this in unit of m naught c square. So sometimes you can use energy units in electron volts, and you can find out the you can find out the relationship between the electron volt and the joule through this relationship. And then of course you can also find out the units relationship between one and electron and between the units of 1.96 into 10 to the power minus 6 times m naught c square. So electron volt in terms of m naught c square is also mentioned over here, and I have given you the idea how you can find out this unit. So in energy units, we normally specify most frequently the units in electron volt, and sometimes in if you want, you can also specify in this units 1.96 into 10 to the power minus 6 m naught c square. But that is in terms of the rest mass energy of the electron. If you want, you can also specify those units also. So you see that I have specified the units over here in terms of that is the spectra could be measured in units of wavelength. That is in wavelength units. Spectra could be mentioned. Spectra could be mentioned in terms of the frequency units. Spectra could be mentioned in terms of the wave number units. As I said, most frequently cited way of representing the spectrum is the wave numbers. You can also specify a spectrum in terms of the energy unit, especially in electron volt. Or if you want, you can also specify the spectra in terms of the rest mass energy of the electron. Now, the optical spectra of the hydrogen atom. So you see that here the full atomic physics evolved from the study of the spectrum of the hydrogen atom. So very fundamental and very important spectrum is the spectrum of hydrogen atom. So optical spectra of the hydrogen atom, and you see that here hydrogen means atomic hydrogen. So this was first reported by Kirchhoff and Bunsen in the mid of 19th century. And these two, that is the Kirchhoff and Bunsen, are also regarded as the founder of spectroscopic analysis. Each element possesses its own characteristic spectrum. So you see that we have many elements, and if you take an atom from those elements, a single isolated atom, and if you study the spectrum of those atoms separately, independently, isolatedly, you will notice that some of the frequencies will match, some of the wavelengths emitted, some structural relevance could be obtained with different atoms, but no two atoms will be identical to each other. So every atom has its distinct spectrum, though it is a possibility that some wavelengths in one spectrum of an element may also match with the wavelengths of some other elements in the atomic spectrum, but that would be a very you see that coincidence. But in principle, an atomic spectrum actually represents the full structure of the hydrogen atom, or you can say that an atomic spectrum is actually a fingerprint or the print of identification of an element. So that's why in order to recognize an element, you need to study the spectrum of such elements. So for example, in few wavelengths, for example, at the maximum can match, but most of the free wavelengths emitted by a substance would be different from the other from those of the emissions of the other atoms. So we can say that the spectrum is actually a distinct. Full spectrum is of course a distinct spectrum of an atom from an element. So each element possesses its own characteristic spectrum. Spectra of hydrogen atom has played a great role in the development of our understanding of the laws of atomic structure and the structure of atom. So once the atomic structure is known, then of course information can be extended for the analysis of the structure of matter. So first of all, atomic structure is very important, that we know the atomic structure of different isolated atoms. Now we have the emission spectrum of atomic hydrogen. And you see that three important lines which are emitted in the emission spectrum of hydrogen atom are referred to as H alpha line, H beta line, and H gamma line. H alpha has a wavelength of 6563 angstrom. H beta has a wavelength of 4861 angstrom. H gamma has a line of 4340, has a wavelength of 4340 angstrom. So you see that we have specified these wavelengths, which we refer to as H alpha line, H beta line, H gamma lines. And these are the three very important lines which are emitted from the spectrum of the atomic hydrogen. Or if you align your instrument towards the outer space, for example close to the region in the sun, you can very easily observe these three wavelengths. H alpha line, H beta line, and H gamma line can be very easily can easily be measured from the space around our solar system, because hydrogen is present over there, and of course the emission of wavelengths from the atomic hydrogen is also present over there, and some of these wavelengths are also reaching, for example, towards the earth, and you can align your instruments towards that space region, and you can measure these wavelengths, for example H alpha, H beta, and H gamma. These are very historically important wavelengths. So H alpha is the most intense, discovered by angstrom in 1853. These three lines are followed by a whole series of further lines which fall closer and closer as the limit H infinity approaches. So you see that if you go to the higher and higher states of the atomic hydrogen, then of course the spacing between the atomic levels becomes smaller and smaller and smaller. And when you reach to this limit, which we call as H alpha, the H infinity limit, then of course the lines are very close to each other, that they will give you an idea or a concept of continuity. And of course there it will be very difficult or hard to have a very precise instrument to measure those wavelengths. But you see that the people have measured these wavelengths up to a level of, for example, maybe above 500. For example, principal quantum number up to 500 wavelengths people have used to measure those wavelengths very precisely. I shall maybe coming to these things later on. But you see that at this topic, it is not the topic to discuss that up to what principal quantum numbers we have measured. So, and even I have not introduced the concept of a principal quantum number as yet. So I should not talk about the quantum numbers as yet up to this point. Now, yes, now let's talk about the Balmer. Balmer is a scientist in 1885 and found that these lines could be extremely well reproduced by the relationship. Which lines? That is these three lines, H alpha line, H beta line, H gamma lines, and many other lines which were known at that time. By the year 1885, Balmer introduced a formula, a numerical formula, that is lambda is equal to n1 square over n1 square minus 4, and this whole in parentheses multiplied by capital G outside that one. So this is a numerical formula. He found that this numerical formula can explain all those wavelengths. And you see that this is one of the achievement at that time, where n1 could take the value of 3, 4, 5, and so on. And G is an empirical constant. So if you use this value of G, which I am not mentioning over here, if you put the value of G over here, and of course with using N1 and 2, N1 equal to 3, 4, 5, and so on, you can put those values over here. You can come out different wavelengths numerically, and you will find that those wavelengths will satisfy, will explain H alpha, H beta, H gamma, and many other wavelengths from the hydrogen atom. So this was one of the empirical and formula that was explaining all the most of the wavelengths coming out from the emission spectrum of the hydrogen atom. When I am talking about a hydrogen atom, it means that so far I am talking, since I am explaining atomic physics, it means that I shall be talking about the atomic hydrogen. So let's manipulate this formula in a very useful form, which is used today. This formula in this present form is not used in atomic physics anymore, but it's a modified form is used. So let's work out the modified form. So we have lambda equal to same one. You see that I have multiplied the numerator by 4. I have also divided by the numerator by G. So 4 over G is present, and 4 and 1 square is also present there. So I have introduced 4 in the numerator and the denominator. And in the next step, I have taken the reciprocal of both sides of this quantity. So you have 1 over lambda over here, and then we have n1 square minus 4 divided by 4 n1 square. And you see that in this formula that was presented by the bomber, here n1 is actually an integer value, and this integer should take a value of 3, 4, 5, and so on. Now you see that in this formula, you can replace 4 over g by a new constant which is called RH constant, and RH is called a Rydberg constant. So this is a Rydberg constant, and you see that if you divide n1 square by 4 n1 square, you will get 1 over 4 over here, and 1 over 4 can be represented as 1 over square of 2. And if you divide 4 by 4 1 square 4 times and 1 square, you will left with 1 over n 1 square. So this 1 over lambda is equal to 1 over the square of 2 minus 1 over the square of n1, and then this parenthesis multiplied by RH, which is called the Rydberg constant. So this formula is the present form. So 1 over lambda is equal to 1 over n square minus 1 over 2 square minus 1 over n1 square multiplied by the Rydberg constant is actually the present form of the Bomber formula in terms of the Rydberg constant, and the value of the Rydberg constant is 4 divided by g is equal to 109677.5810 centimeter inverse. So this is now the formula of the present shape of the formula is now being used in atomic physics, and this is that is the original formula of the bomber is no more used, but its modified form in terms of the Rydberg constant is being used now today. And this was worked out by the bomber. So this explains the series from the bomber formula. So this formula, which I have written as 1 over 2 square minus 1 over n square, where n1 starts from the value of 3, 4, 5, and so on. This formula is referred to as the bomber formula, and the series of wavelengths which are generated by this formula is called the bomber series. Later we shall see that if you use different value of over here in the first place, that is 1 over 2, the square of 2 is replaced by the square of 1, or by the square of 3, by the square of 4, by the square of 5, then of course you will give it different names. For example, Lyman series, if you have the square of 1, if you use 3 instead, then you have a different square. For example, maybe bracket series, and then other series will come out, which we shall be familiar in the today's lecture. So you see that this you may consider the this formula, that is this numerical analysis at that time in the year 1985 to be a breakthrough in the analysis of the emission spectrum, because all the emission spectrum of the hydrogen atom can be generated through this formula, which was initially known as a bomber formula, but now a different series of wavelengths can also be coming out as an emission spectrum from the hydrogen atom can also be explained with this formula using a different index at the initial place, that is 1 over the square of 2 can be substituted by 1 over 1 square, 1 over 3 square, 1 over 4 square, 1 over 5 square, and so on. And this then the resulting formulas will explain the all spectrum of the hydrogen atom, that is the all emission spectrum for the hydrogen can be explained. Now you see that here I am tabulating different wavelengths over a different series from the formula. So since I have introduced the bomber series formula given for the value of 2, because you see that here I have n prime is equal to 2 and n prime mean the value of the first index. For example, this n, the first index I over this place can be represented as n prime, and this n n1 here can be represented by single n over here. So I am introducing two variables, n prime on the to be changed along the horizontal direction, and n will change vertically downward. This n prime is actually the same value of n as I have mentioned over here, n1. So n1 is now substituted as n prime, and this for example in the first place, which I have 1 over 2 square, the square of 2, this 2 will be replaced by another constant, another general integer value which is represented by n. So we have 1 over n square minus 1 over n prime square multiplied by the Rydberg constant. So here in the Barber formula, you would notice that I have this formula. This is the Balmer formula, Rydberg constant multiplied by 1 over the square of 2 minus 1 over the square of n. So you see that this formula, and here you see that I am representing this formula in this form. So you see that 2 here, 2. You can see the index 2 over here, and this 2 has appeared in the first as a first term in the parentheses. You can see 2 over here, and in the next formula 3 is over here. In the next formula is 4 over here. In the first formula 1 over here is over here. So you see that these values of n prime, that is 1, 2, 3, 4. You see that these are appearing at the first place in these parentheses. So 1 over 1 square, 1 over 2 square, 1 over 3 square, 1 over 4 square, and correspondingly we have the series which we are referred to as the Lyman series, Balmer series, Bastian series, bracket series. And you see that we are specifying here the wavelength in terms of centimeter inverse. And the other index is also changing downward because it will give you the different wavelengths from the different levels. So you see that this will form the ground level. For example, as far as the Lyman series is concerned, this index 1 says that we are talking about the ground state of the hydrogen atom. And with these 2, 3, 4, 5, and 6, these correspond to the higher levels in the as far as the Lyman series is concerned. So for the Lyman series, the next higher level is this level, which corresponds to n is equal to 2. The third level corresponds to n is equal to 3. The fourth level corresponds to n is equal to 4. The fifth level corresponds to n is equal to 5 for the Lyman series. And for the Balmer series, the ground state for the Balmer series will be 2. And because this represents the level number 2 of the atomic states of the hydrogen atom, so this is the Balmer series, and you can see that the level number 2 forms the ground state of the Balmer series. The next higher state as far as the Balmer series is concerned will correspond to n value of n equal to 3, value of n is equal to 4, value of n is equal to 5, and so on. And similarly for the Bastian series, the ground level for the Bastian series will correspond to the value of 3 over here. You can see that for the Bastian series we have the first index is equal to 3. It means that the 3 will be regarded as the basic level for the Bastian series, and for the Bastian series you will notice that the next higher level above the Bastian ground state will correspond to the quantum will correspond to the integer value equal to 4, and the next to that one is will correspond to the n value corresponding to number 5. And similarly for the bracket series, you can see that the ground level for the bracket series, or the ground level for the bracket series, will start with the value of n prime is equal to 4. And the other levels, for example, n for the bracket series will be, that the n for the bracket series over here will be greater than 4. So it will be 5. For example, it will start with from 5. So you see that if you are talking about the Lyman series, in which the first level is the ground level, then n will start from 2, 3, 4, 5, and so on. For the Balmer series, the second level is regarded as the ground level for the Balmer series, and the next levels to those one will be will take the value of n equal to 3, 4, 5, 6, and so on. For the third series, which we have the Bastian series, and for the Bastian series, the level number 3 will be regarded as the ground level for the series of the Bastian, and the next level will correspond to the value of n equal to 4, 5, 6, and so on. And for the bracket series, the ground level corresponding to n prime is equal to 4 will be considered as the ground level. The next higher level for this series will correspond to value of n equal to 5, 6, 7, and so on. So these are the series that I have given a brief introduction. And the year of discovery, YOD, stands for the year of discovery. For the year of discovery for the Lyman series was 1906. For the Balmer series was 1885. For the Bastian series it was 1908, and for the bracket series it was 1922. So you see that the first was discovered by the Barber in 1885, and the formula was given like this one. And later on, the other scientists, for example, the Lyman, the Pasteur and the Brackett and the other scientists, then they started their investigation, and of course they observed the different values of the different wavelengths from the emission spectrum of the hydrogen. And then of course different wavelengths was also they tried to fit them into the formulas similar to the Barber formulas, and they correspondingly found these formulas over here for different values of the indices. And then of course the basic formula was given by the Balmer. So now let me talk about different wavelengths coming from that one. For example, this is the wavelength that is coming out, that the first wavelength of the series of the Lyman. So it means that now you see that these are the integer values. For example, I am using n and n prime are as the integer values. Now at that time when these formulas were used, these were regarded as the integer values. But now today we know that these are the principal quantum numbers. So these integer values n are actually the principal quantum numbers. So from now on we shall be talking about n to be as principal quantum numbers. Now also these take the integer values, for example 1, 2, 3, 4 and so on, and these will be regarded now from now onward as the principal quantum number. So you see that the Lyman series, in which there is a transition from the quantum state number 2 to the quantum state number 1. So when the hydrogen atom emits light from its state number 2 to the state number 1, that is from the level number 2 to the level number 1, it will emit this wavelength, which is 82257 centimeter inverse. So when the hydrogen will make its transition from the third level to the first level, because this is the Lyman series in which level 1 is regarded as the fundamental level. So if the transition takes place from the third level to the first level of the first level, then of course this wavelength is emitted, which is 97466 centimeter inverse. And if the transition in the hydrogen atom takes place from level number 4 to its ground level, that is the first level which we in the of the Lyman series, then of course this wavelength will be emitted. And for the fifth, if the transition takes place from the fifth level to the first level, or the first level of the Lyman series, then of course this wavelength will be emitted. For the Balmer series, you will notice that the transition will take place from the level number 3 to the level number 2. So if the transition of the in the atomic spectrum takes place by the hydrogen atom from the level number 3 to the level number 2, then of course this wavelength, which is 15233, will be emitted. So if the transition from the level number 4, which is to the level number 2, takes place, then of course in the emission spectrum of the hydrogen, this wavelength will be noted 20565. And if the transition from the fifth level of the hydrogen atom will takes place to the level number 2, then of course this wavelength, which is 23033, will be emitted. For the Pascal series, the basic level is the level number 3. So the transition will takes place, the first transition of the Pascal series will takes place from the level number 4 to the level number 3, and then this wavelength, which is 5333, will takes place. And if the next higher transition will be from the level number 5 to the level number 3, so this will form the second transition of the Pascal series, will give you a wavelength of 7801. Now for the bracket series, the fundamental level with the level number 4. So the first transition will takes place from level number 5. So the transition will takes place, if takes place from level number 5 to the level number 4, then the first wavelength corresponding to the bracket series will takes place as 2467 centimeter inverse. And you see that the year of discovery of these brackets of these series have been given. So now we shall be talking about Lyman series, giving you many wavelengths, out of which I have shown only the transmission up to the fifth level of the hydrogen atom to the ground levels. I have shown the different transitions for the Lyman series, for the Balmer series, for the Pascal, for the bracket, and so on. There are some other series which I have not mentioned. Now you see that if you subtract this quantity from this quantity, which I have shown with with an arrow sign and also with a negative sign, you will see that if you subtract these two one, you will get a wavelength, for example this. So subtraction of these two these are the wavelengths, and if you subtract the two one in frequency domains, for example, you will get a frequency corresponding to this one. Or you can also subtract the wavelengths in order to find this wavelength, for example. So now let me explain this one. This wavelength, which is given corresponding to the principal quantum number 2, which is 82257. This can be obtained from using this formula of the Lyman series. So this is a formula of the Lyman series. You have the Rydberg constant, you have 1 over 1 square minus 1 over 2 square. So it means that now this 2 as a second term indicate that you are talking about the transition from the state number 2 or level number 2 of the hydrogen atom to the level number 1. So this transition is from level number 2 to the level number 1, and if you put these values over here, that is, if you put the value of Rydberg constant and evaluate this one, you will get this wavelength. And if you want to obtain this wavelength, what you need to do is that you need to use this formula of the Lyman series, in which the first term is the same and the second term has changed, because here you are using n is equal to 3 for the quantum number for the transition from the level number 3 to the level number 1. So this indicates this is again the formula in the Lyman series explaining this blue wavelength corresponding to the quantum number 3. So I have shown this formula also in blue. So this states that this is the transition of in the Lyman series from the state number 3 to the state number 1. So if you put the value of Rydberg constant and evaluate this one, you will get this wavelength, which is 97466. And you see that I have shown red wavelengths using the Lyman series formula given in red. I have used this blue wavelength. I have explained this wavelength using the Lyman series formula given in blue. And now if you subtract these two formulas, one given in red, one given in blue, and you see that this is given over here. So Rydberg constant, and you have in the parentheses 1 over 1 square minus 1 over 3 square, which are the blue terms from the blue formula, and then you have these two terms in the red, which is 1 over 1 square plus 1 over 2 square. Due to the subtraction, you have a plus sign over here, and then you see that this is the formula from the red. And if you subtract this one, you see that the first term in blue will be cancelled with the third term shown in red, and then of course rearranging these terms in green in green formula, you will get Rydberg constant, and with the parentheses you have 1 over 2 square minus 1 over 3 square. And you see that this formula is actually the Balmer formula, and you see that this explains the green term over here. So you see that subtraction of any two wavelengths will explain the wavelengths from the next wavelength of that series from the next series. For example, the difference of these two consecutive wavelengths in the Lyman series formula can give you a wavelength of the Balmer series formula, and this is what I have explained. And this is also known as the Ritz principle, Ritz combination principle, which we shall explain next. So I think that I have given enough information about this table. So you can have Lyman series, you can have Balmer series, you can have Paston series, you can have bracket series, and other series of similar formulas using different indices in those formulas as given over here, shown in red, blue, green, and purple. You see that all these formulas can now be summarized, can now be combined in a single formula. For example, nu bar is equal to 1 over lambda is equal to Rydberg constant, and within the parentheses we have 1 over n prime square minus 1 over n square. And you see that this n which appears in the second term is always greater than n prime. So n is always greater than n prime, as you have seen in these formulas. In the n position, n is always greater than the value. For example, in this formula, n is greater than 4. In this formula, n has to be greater than 3. In this formula, that is in the Balmer formula, n has to be greater than 2, and in the Lyman formula, n has to be greater than 1. So we have combined all these formulas into in a single formula over here. So this is the fundamental formula explaining all the above series that we have mentioned, and the integers n prime and n are now referred to as the principal quantum numbers. So we can explain all these, we can combine the formulas corresponding to all these series: Lyman series, Balmer series, Paschen series, Beckett series. All these formulas and also the other series which I have not mentioned can be combined into this a single formula, which is given as nu bar is equal to Rydberg constant times 1 over n prime square minus 1 over n square, with the condition that n is always greater than n prime. So with the different greater values of n, with the fixed value of n prime, you can generate the whole series. For example, setting n prime is equal to 1 and changing n prime to 2, 3, 4, 5, and so on, you can generate the full Lyman series. Now you see that I have also slightly explained the Ritz combination principle while I was explaining the difference between any two consecutive wavelengths can be used to generate to generate a wavelength in the next layer, in the next series. So it means that subtraction of any two can also be used in the generation of the wavelength in the next series, because of course, as I have mentioned over here, that you have the Lyman formula in red, Lyman formula in blue, and the subtraction of these two wavelengths will give you the wavelengths in green, which belongs to the Balmer formula. So you see that similarly you can subtract different you can have different subtraction and you can generate different wavelengths. This is called the Ritz combination principle, which I am going now to elaborate over here. The difference of Ritz combination principle says the difference of the frequencies of two lines in a spectral series. That is, we are talking about the difference of frequencies in the same spectral series. That is, the difference of two frequencies from the Lyman series. We cannot take the difference from the Lyman series and the Balmer series. So this explains that the two lines should be belong to the same spectral series. So the difference in the frequencies of the two lines in the same spectral series is equal to the frequency of a spectral line from the same atomic spectrum. So hydrogen spectrum, for example, if you are studying the hydrogen spectrum, then the difference of frequencies from the same series can give you a spectral frequencies of the same atomic spectrum lying somewhere else. For example, the difference of these two may be lying anywhere between them. For example, the difference of wavelength corresponding to n is equal to 2 and the wavelength corresponding to n is equal to 5 will give you a different wavelength in the series corresponding to a series of the spectrum, corresponding to a line in the series of the spectrum. So that's why the difference of frequencies of two lines in a spectral series is equal to the frequency of a spectral line from the same atomic spectrum. Maybe in the next higher formulas, for example, in the next higher series. In the energy spectrum of the electron in a hydrogen atom, any spectral line or the frequency can be represented as a difference of two terms of the form Rydberg constant divided by n square. So you see that if you take a difference of two terms of this form, then of course you can generate the other terms. For example, you can see that I have taken the differences of the form of this term, that is the Rydberg constant. You see that here 1 over 1 square will be cancelled by 1 over 1 square, and then of course you are left with the difference of the difference of two terms of the form of RH divided by n square. So if you take a difference of two terms of this form with a different value of n, then of course you will generate some other wavelengths, some other spectral lines in the spectrum of the hydrogen atom corresponding to maybe of the same series or maybe corresponding to a different series. So in the energy spectrum of the electron in a hydrogen atom, any spectral line or frequency can be represented as a difference of the two terms of the form RH over n square. And of course, this difference is also prominent in the formulas over here. You see that we have the difference of these two terms in each formula. You can notice. Okay. In the term diagram of the lines of hydrogen spectrum given on the second next page, energy is sometimes plotted in units of centimeter inverse, and the relation of the electron volt and the centimeter inverse is given. So you see that here I have used the term diagram, and this diagram I am presenting soon. In the next slide, I am presenting the term diagram. So you should wait unless I explain this term diagram. So the term diagram of the lines of the hydrogen spectrum will be explained shortly. And for that one, I am using, you see that there you could use a term of the centimeter inverse. That is, the energy can be represented in centimeter inverse using a formula of the form which is given E is equal to H nu. You see that E is equal to H nu is the formula that can be used to calculate the energy of a photon. So you can modify this formula as H into C over lambda, because you can replace nu by the value of by C over lambda. And then you can keep H and C on one side, and 1 over lambda can be substituted by the wave number represented by nu bar. So you see that E is proportional to the nu bar. That is the wave number. So the wave number can be specified, since it is a reciprocal of 1 over lambda, it can be specified in terms of units of meter inverse, and this energy on the left hand side can be represented in joule. So we can have a relationship between joule and meter square and meter inverse, and later we can also modify this to electron volt. For example, the energy in joule or can be specified in electron volt. Similarly, nu bar in meter inverse can also be represented in centimeter inverse. And then the relationship between electron volt and centimeter inverse can be worked out. For example, here we are giving you the relationship E is equal to H nu, and again you see that I have specified that it can be written as H into C over lambda. So Hc can be kept on one side in the set, for example, E is equal to Hc, and then we have 1 over lambda. You can specify the value of H over here, which is the Planck's constant, and its value is given by 6.62607015 times 10 to the power minus 34 joule second. And then we have the C in terms of the meter per second, 3 into 10 to the power 3 into we have 3 into 10 to the power 8 meter per second is the speed of light in vacuum, and then we can using 1 over lambda to be equal to 1 meter inverse. So here I am using the value of lambda as 1 meter, so 1 meter inverse is being used over here. So you see that if you multiply all these quantities, you will get E equal to 19.878 into 10 to the power minus 26 joule. And you see that this energy of joule corresponds to when we have used the wavelength equal to 1 meter, or 1 over lambda, or wave number will be given as 1 meter inverse. So here you can say that this energy, that is the energy equal to 19.878 into 10 to the power minus 26 joule. This energy corresponds to the wave number equal to 1 meter inverse. So you can say that 1 meter inverse is equal to 19.878 into 10 to the power minus 26 joule. You can represent 1 meter inverse as 10 to the power minus 2 centimeter inverse, because in 1 meter there are 100 centimeters, because there are 1 meter can be written as 10 to the power minus 10 to the power 2, and since there is a negative sign over here, we can represent it as 10 to the power minus 2 into centimeter inverse, and you can represent joule as such over here. And in the third step, you can represent you can substitute joule in terms of a value, in terms of its value in electron volt, which is 6.242 into 10 to the power 18 electron volt. So if you multiply these two quantities, you will get 124.0789 into 10 to the power minus 6 electron volt. So 1 centimeter inverse is equal to this much electron volt. So this is the relationship of the electron volt in terms of the centimeter inverse in terms of electron volt. So 1 centimeter inverse is equal to 124.0789 into 10 to the power minus 6 electron volt. And you can take the reciprocal of this relationship, that is, you can solve this relationship for the value of 1 electron volt, and this is what we have done in the next step. So 1 electron volt is equal to 1 over 124.0789 into 10 to the power minus 6. In this is in the denominator, and we have centimeter inverse in the numerator. So you see that if you carry out this numerical evaluation, you will get one electron volt is equal to 8059.44 centimeter inverse. So this is what you can represent energy in electron volt through this relationship to the energy in centimeter inverse. So in centimeter inverse is also a unit of energy, because as I have mentioned earlier, that centimeter inverse can also be used as a unit of energy in wave numbers. So this is 1 electron volt is equal to 8059.44 centimeter inverse. But you see that I have not used very precise values of these numerical values. For example, the value of the Planck's constant and the value of the velocity of light is not given in up to very high precision. So if you use very precise values of these two quantities, that is using accurate and higher precision values of H and C to a greater precision value, you can find that this 1 electron volt is equal to 8065.54 centimeter inverse. And if you round out this value, then you can write that 1 electron volt is approximately equal to 8066 centimeter inverse. So this is the relationship that we have worked out. So you can represent your spectra either in terms of electron volt, or if you want to represent it in terms of the wave numbers, you can use this relationship to convert the energy in terms of the wave numbers. Now we are coming to the term diagram of the lines of the hydrogen spectrum. You see that I have this quantum number n. So this quantum number n is actually this number. For example, in this formula, you can identify the value of n over here, which is appearing in the second term, and n prime is appearing in the first term. So for a given series, n prime will be fixed. For example, for the Lyman series, n prime is equal to 1. But n will change from 2, 3, 4, and so on. For the Balmer series, n prime will be equal to 2, which will be fixed for the whole series. And n will then change from 3, 4, 5, 6, and so on. And similarly for the other series, n prime will be fixed, whereas n will take the values according to this relationship, integer values. So I have shown those values over here. So these are the n values, which can take higher values, whereas n prime values will be fixed for each series. So I have the 0 over here, 0 reference line over here, which means that this level corresponds to okay, and then I explain this one. You see that I have shown the energy on the vertical side. This is the energy in terms of 10 to the power 3 centimeter inverse. That is, we are using these values of energy being expressed in terms of the wave numbers. So we have these values of energy 0, 10, 20, 30, and so on up to 80, and then ultimately 110 in terms of the wave numbers, in terms of this 10 to the power 3 times centimeter inverse. So these are the values in terms of these are the values of energy in terms of the wave numbers multiplied by 10 to the power 3. You can assume these energies to be the bound state energies. You can represent these energies as the negative energies. You know that in an atom, all the energies are in the bound state. That is, the electron energies are bound energies. That is, you can represent those energies in the negative form. And outside that, an atom, for example, beyond this level, the atom has no energy. That is, the atom is neutral. Within the atom, different states exist at different bound states. So those bound states have negative energies. So you can represent either these energies in the negative form, or you can also set your reference at the ground state, and the energies can be then set, positive energies can be set upward. So then the ground state will energy, if you set over zero, reference point over zero over here, then it means that you are representing the energy in its lowest energy state by the zero energy. So the other states in the atom or the other levels in the atom will then exist at higher energy state, and you can draw those energies positively in the upward direction. But you see that here I am using these energies of these states in the bound states, energies of the different states corresponding, and these energies are actually the negative energies. And here I am plotting the principal quantum number n. So you see that when you increase the value of n, what will happen? What will happen? You see that when n is equal to 1 over here, n is equal to 2 over here in the Lyman series, you will see that the gap between these two consecutive levels is much greater. But the separation between the level 2 and 3 is shorter, is relatively shorter. And then the difference between 3 and 4 is even shorter. The difference between the spacing between the levels 4 and 4 is even shorter, and so on. Unless you will see that when n is very large, these differences will keep on decreasing, and ultimately the separation will become so small that we cannot identify separate levels, and then we shall reach to the value of the continuum. So when n is very large, up to infinity, it means that the levels are so narrowly spaced, our instruments cannot separate those levels, cannot identify the individual levels, and then we have the continuum. So this continuum is represented by this bold line over here. So now let's talk about these series. For example, this is the ground state I have represented, and this is level number 1. So for the Lyman series, the level is fixed. That is, the initial level is Lyman in the Lyman series is the level number 1, and all the emissions and all the wavelength emission will be in the UV, in the ultraviolet frequencies. So the first transition on the left hand side for the Lyman series I have shown from level number 2 to level number 1. The next one is from level number 3 to level number 1. The next one is from level number 4 to level number 1, and so on. So you see that I have represented someone, and then you see that I have shown a gap over there. It means that I have not shown all the continuous spectrum. Then of course, ultimately the final spectrum for which n is infinity, I have also shown that line over here. So this is the Lyman series. Now let's talk about the Balmer series. In the Balmer series, the ground level for the Balmer series is the level number 2. So all the transitions will come from the higher states to the state number 2 will be observed in the Balmer series, and this V stands that all the transitions will be in the visible. So in the Balmer series, all the transitions will be in the visible range of the spectrum. So you see that here you can see that the first transition on the left is from level number 3 to the level number 2. That is, the hydrogen atom will decay from the state number 3 to the state number 2 and will emit a wavelength. Similarly, the transition or the decay of the hydrogen from level number 4 to level number 2, then from level number 5 to level number 2, and so on. So then from infinity to level number 2. So all these wavelengths in the series will form a Balmer series, will give a wavelength usually in visible light. Then we have the Paschen series, and the base level for the Paschen series is the level number 3. That is, the Paschen series corresponds to the emission of hydrogen spectrum from all the higher states to the state number 3 or the level number 3 of the hydrogen atom. So the first level from the left is from state number 4 to the state number 3. Then the next one is from state number 5 to state number 3, and so on. And then the last one is from state number from n is equal to infinity to the state number 3. Then we have the BRKT, that is the bracket series. And you know that in the Paschen series we have the infrared transmission in the infrared. represented as IR. Then we have the bracket series, and the base level for the bracket series is the level number 4, and all the transitions from the higher states, from the higher levels to the level number 4 will occur, and then the resulting series will be referred to as the bracket series. The emission of a wavelength will be in the IR, will be in the infrared region. And then we have the next one, the last series that we are going to describe is the fund series. And in the fund series, the ground level is the level number 5, and all the transitions from the higher level of the atomic spectrum to the level number 5 will contribute different wavelengths, forming a fund series. And in the fund series, of course, the wavelengths will be in the infrared region. So you see that I have explained all these Lyman series. I have explained the Lyman series, that is the transition from all the higher atomic levels of the hydrogen spectrum to the level number 1. Balmer series from all higher levels to the level number 2. Austin series from the transition from the all higher levels of the atomic hydrogen to the level number 3, and similarly for the other rest of the 2 series. I hope that the description will be understandable. And now I am going to specify different wavelengths emitted in the Lyman series. So in the Lyman series, from the left one, I have this wavelength, which is 1 to 150.7 angstrom. The next wavelength, that is from the level number 3 to level number 1, is 1025.7 angstrom. Then from the level number 4 to level number 1 is 972.5 centimeter, and so on. And then from the infinity to the level number 1 is that is 911.8 angstrom. And similarly for the Balmer series, I am representing these wavelengths in red, and the first one corresponds to the emission of a wavelength when the transition from the level number 3 to the level number 2 takes place in the atomic hydrogen. Then of course this wavelength is Bayer, which is 656.8 angstrom. And similarly the next wavelength in the Balmer series, that is from the level number 4 to the level number 2, will give you a wavelength of 4861.3 angstrom, and so on. And similarly other spectrum can also be explained for the Balmer series, for the Austin series, for the bracket series, for the fund series. So these are the wavelengths that I have shown as a line in these series, and corresponding to these lines in the series, I have also mentioned the corresponding wavelengths given over here. And you see that here we are talking about the emission spectrum of the hydrogen. So these all the lines correspond to the emission spectrum of the hydrogen. That is, the hydrogen atom has absorbed some energy from somewhere from its surroundings, and it has emitted the photon in some direction, and from that one we have measured that one. For example, in the stellar space, where hydrogen atom in atomic state may be in abundant, those hydrogen atoms in atomic state can absorb energy from its surrounding, and can re-emit those energies in different directions, and some of the energy can also reach to the ground. And if you are in the ground or on the earth, and you are aligning your instrument upward towards the stellar hydrogen, you can measure these spectra from those ones. So these are the emission atomic spectra from the hydrogen atom. Now you see that I am also explaining another spectrum chart, which is called the hydrogen spectrum in terms scheme of the Grotrian. So this is the Grotrian way of representing the hydrogen spectrum. So Grotrian means that you represent different atomic states. The separation between different atomic states versus the principal quantum numbers are represented as a graphical way of representation of those atomic levels is the representation in terms of the Grotrian. So Grotrian, you see, that is the historical way of representing the hydrogen spectrum. On the left hand side, you see that I have the excitation energy of this one in terms of the electron volt. Here excitation energy means that we are giving energy to the hydrogen atom, and we are exciting the hydrogen atom to the different levels by giving the energy. So that energy is called the excitation energy, and we are specifying that energy in electron volt. And on the right hand side, you will see that we have the wave numbers, and the wave numbers are shown in the units of centimeter inverse. And you see that the wave numbers will decrease downward because we are specifying the wave numbers 0 at the top, and so multiplied by, we are representing the wave numbers multiplied by the parameter 10 to the power 3. So this is the multiplier for all the values of the wave numbers, and since we are representing the wave numbers at the top to be equal to 0, so the wave numbers will decrease downward, whereas the electron excitation energy, since represented upward, so it will increase upward. So this is the hydrogen spectrum in the term scheme of the Grotrian. So this is the ground level of the hydrogen. This is the ground state of the hydrogen atom. So when when the hydrogen atom has not absorbed any energy from anywhere, it will be in its ground state, that is, it will be in this state. So this is the principal quantum number 1 state. So the hydrogen atom is in this state. So if you provide energy to the hydrogen atom, you can raise the hydrogen atom from this state to the other states. You see that in those states we have mentioned that if the principal quantum number is 1, then you can excite it to the other levels with the different principal quantum numbers. So you can excite the hydrogen atom to this quantum number 2. So principal quantum number 2 has 2 levels over here. Principal quantum number 2 has 2 levels. You can see that there are 2 levels corresponding to the principal quantum number 2. And you see that I have mentioned that this is n value, or the principal quantum number values. So there are 2 levels shown over here corresponding to the principal quantum number 2. There are 3 levels shown to the principal quantum number 3. There are 4 levels shown against quantum number 4, principal quantum number 4. There are 5 levels corresponding to the quantum number 5, and so on. And you see that here I am not explaining why there are 2 levels corresponding to the principal quantum number 2. These will be explained in the rest of the atomic physics. And similarly, I am not going to explain why these are 3 levels corresponding to the quantum number 3. So these will be explained in the rest of the atomic physics. So you see that here just I want to explain that I want to excite the atom, hydrogen atom. I can give an energy to the hydrogen atom from its states corresponding to the principal quantum number 1, and I can raise the hydrogen atom to one level of the principal quantum number 2, which I have shown this level. So I can also raise this hydrogen atom to the other levels, but not to the levels, all the above levels corresponding to the principal quantum number 1. So this is not possible. So all the transitions from the ground state can done to the all higher states of the principal quantum number 1, but not to the state just above the principal quantum number 1. That is, I cannot raise to the left level shown corresponding to the principal quantum number 2. I cannot raise the hydrogen atom. I cannot excite the hydrogen atom from the principal quantum number 1 state to the left level of the principal quantum number 3 state. I cannot raise the hydrogen atom from the level number 1 to the left, to the level on the left corresponding to the quantum number 4, 5, and so on. But I can raise it to the principal to the level shown on the right hand side of the principal quantum number 2. Similarly, I can also shown to the above levels over there. So even I cannot raise the hydrogen atom from this first level principal quantum number first to the level number 3 of the principal quantum number 3. So this is also not possible. That is, I cannot raise the hydrogen atom from ground state number 1 to the level number 3 on the rightmost side corresponding to the principal quantum number 3 of the hydrogen atom. I cannot raise the hydrogen atom to that state because this is forbidden. This is optically forbidden. And the rules that determine those forbiddens are referred to as the selection rule. Selection rule permits that which rule give you the way that you can excite the hydrogen atom to different levels. Those rules are called selection rules. And under those conditions, under the section rules, we can have two type. We can have allowed transitions, and the allowed transitions are delta L is equal to plus minus 1. So here delta L is an integer that should vary for the values of a plus minus 1 for the transition to take place. So if delta L is not obeyed by this number, then of course the selection will not be allowed. That is the transition will not be allowed, or the transition violating this value of delta L will be forbidden transition. We can say that optically forbidden transition. So you see that then from the level number 2, on the left hand side, you can excite that one to other levels, not the level number 3, 4, 5 above to the level on the left hand side of level 2. Similarly, you have a level on the right hand side of level 2. You cannot raise the hydrogen atom from this level to all the above levels above it, but you can raise it to the neighboring above levels. For example, you can see from the level number 2 on the right hand side of a principal quantum number 2 that the transitions are shown in the red to different levels. Similarly, you can see that I have shown these levels following these lines. I have shown according to the selection rule given as delta L is equal to plus minus L plus minus 1. And where is the delta L? Where is the values of L? The values of L have been shown on the top. So L is equal to 0, L is equal to 1, L is equal to 2, L is equal to 3, L is equal to 4, and so on. And I have also shown another integer which is called K. K is equal to 1, K is equal to 2, K is equal to 3, K is equal to 4, K is equal to 5. But you see that I am not talking about the parameter K. I am just talking about the parameter L. So L is shown over 0, 1, 2, 3, and 4. For example, for the transitions on the leftmost side, we have L is equal to 0. In the middle, in the next one, L is equal to 1. In the next is L is equal to 2, and so on, for so on. So you see that the transition is the only transition allowed is delta L is equal to plus minus 1. That is transition of the level with the same value of L is not allowed. That is a transition from the levels from L is equal to 0 to the other levels for L is equal to 0 is not possible. Similarly, transitions from a level with L is equal to 1 to all the other levels with the same value of L are not possible, because then delta L will be equal to 0. And similarly, when L is equal to 2, then the transition from any level corresponding to L is equal to 2 to all other levels of L is equal to 2 are not permitted, because under that condition, delta L will be equal to 0. And you see that delta L will be equal to is not allowed, because the delta L has to be equal to plus minus 1. Similarly, for example, you cannot make the transition, for example, from any level 1 to the level number 3. For any level corresponding to the value of L is equal to 1 to any level, for example, corresponding to the level 3 is not possible, because the delta L will then be equal to 3 minus 1 will be equal to 2. And you know that the selection rule allows you that delta L should change only by delta L is equal to plus minus 1. So this is important for the spectrum of the hydrogen atom. So you see that many other levels are possible. So this level L is an integer value starting from 0, 0, 1, 2, 3, and so on. And this K is a number starting from integer values of 1, 2, 3, and so on up to 5. In the next few slides, I shall be explaining these numbers L and K, because later on I have not given these numbers any value, but later on we shall see that these are also recorded as the quantum numbers. So at present, you should not confuse yourself with the quantum numbers. You should just take them as integer values. L starting from 0, K starting from 1. And the selection rule for the emission spectrum of this hydrogen atom is equal to delta L is equal to plus minus 1. Only transitions obeying delta L is equal to plus minus 1 will be allowed, other will be forbidden. So you see that this was all about the hydrogen spectrum in the term scheme of Grotrian. And this is the end of the first slide of the atomic and molecular physics course.